Great. Well, welcome on this Monday morning. What's today? The 23rd of May. That reminds me, we don't have a CNS talk this week because it's a public holiday in a lot of countries across Europe on Thursday. So no talk on Thursday, but we're going to be back with the CNS talk in June. Now, welcome to Neuroccino, exciting week in science, where we review papers that we come across and thought they're worth sharing, they're interesting of some sort, and sometimes we even branch out, like last week, to non-directly brain sciences. And the rule of the game is everyone is welcome to present. So if you read something, just ping me a text or a tweet or whatever. Let me know that you want to have the slot, and then you can come in and present your paper. I shared the link for today's paper with you in the chat already. And I was trying to wait until everyone was in the room, so I hope you can all see it now. But basically, today's paper is a review by the HEBA lab, where they looked at postmortem mapping of connectional anatomy for the validation of diffusion MRI. Let me just share the screen so you can see it. Here we go. Now, this paper is interesting because we often assume that we know anatomy, that there's nothing new to discover when it comes to anatomy. But in fact, we're missing the gold standard. There's many definitions of anatomical features on the surface of the brain or the connections of the brain, where we don't actually know what the true anatomy should be like. And one of the reasons for this is that we don't have a gold standard. For a while, we thought we had a gold standard, but actually it turns out that the gold standard for tractography, which used to be postmortem Klingler dissection, actually suffers very much the same limitations as tractography. So this review tries to have a look at all the methods you can use to validate diffusion imaging tractography. And it describes the methods, it says what's good about them, it says what's bad about them, and it makes the link to diffusion imaging in terms of how it helped validate or not validate measures of tractography. And that could be the actual reconstruction of the tracts in terms of the areas of origin and termination or topographic organization of the tract. It could be the fiber orientation. So for example, when they're crossing and you have different peaks of fiber populations with tractography. And then it also looked at the validation of the microstructure, so extracting indices from diffusion imaging and correlating those with postmortem measures. Now, the conclusion of the paper is that no method is perfect, certainly not tractography, but also all the methods that we have to validate tractography are not perfect. There is not a single method that you can just apply, push a button, and there you go, you have your validation. That's sadly not how this works at the moment. The other thing is that all the methods they discuss require anatomical knowledge. So again, it's not an easy, oh, I'm just going to apply this and it's done. No, you really have to know your anatomy. And I'm going to show you the figures in a second. There's some images where even I reach the limits of my own anatomical understanding for them. I love the shocked face. Yeah, that happens sometimes, but it's histology. So I'm going to show you the example in a minute. They also conclude that we often use the methods in a complementary fashion, but they're often applied on different specimens. So often we acquire diffusion imaging in the vivo brain, for example, or even postmortem. But then the validation method, the track tracing, or the staining is done in a different specimen. So they really, really make the point that we should try and collect the different kinds of methods in the same sample to really have a within sample comparison. And then they also highlight a couple of issues in terms of the registration process between the methods. And I reviewed a paper recently on a unified MR histology map, so you can go back to that one and have a look as well. That discussed some of those issues as well and solved some of them. And also how when you do staining, for example, you need to slice thin layers of the brain. That introduces distortions. If you do clarity, and I didn't actually notice, but if you leave the specimen, it increases in size by 300%, so you don't need to reduce it again. And then obviously the mismatch in resolution, because tractography is still limited by the resolution of the MRI scanner. Now, ex vivo, we can obviously push that down to a couple of microns or hundreds of microns. But with histology, we can go a lot more into detail, and then we need to match our scales as well. So these are a couple of the points. I'm not going to go into the details of it because it's quite a rich review, but they also make the point that the availability of the HCP was a game changer, because it really pushed what we can do with our data for the time being. So I said I wanted to show you a couple of the images. So here they start with the history of ex vivo diffusion MRI and what to pay attention to. One of the things, for example, is that the decrease of diffusivity in the fixed tissue must be offset by an increase in the B values achieved with stronger diffusion weighting gradients and longer durations, but then that comes at the expense of having more eddy current distortions in your data, for example. So they also make the point that there is no fixed solution. Like, they can't give you a recipe to have the perfect acquisition for your data, but it always depends on the kind of data that you have and the question that you're trying to address. Now, what's really nice is they have those summary tables throughout the paper, where they highlight the good and the bad about each method. And one that I thought was quite striking is table 2, where you can see that really the only method available in the living human brain to track the connections between areas is diffusion imaging. So at the moment, there is no other alternative. And then when it comes to the validation, for example, we often use anatomical tracing, track tracing, but that, for example, cannot even be applied to the human brain. This is an animal-only method. And then we have this whole new set of problems about which areas are homolog between us and us being primates in general, and the comparative comparison between brains. So track tracing, they say, has between 60 and 70% sensitivity with diffusion imaging. And then here you have an overview of all the settings that we used for those studies that attempted a validation with diffusion MRI based on the B value, the gradient interactions, and the voxel size. And one thing that is immediately evident here, even if you have no idea about diffusion imaging, is that there is a huge range in numbers. So if we look at the gradient directions, for example, we have as little as 6 directions and as many as, 514, which obviously is a huge range and will impact the data quite a bit. And then we can also see with the diffusion weighting in the data, the B value, we have quite a huge range. And also for the voxel size, you can see how that is sometimes larger and sometimes smaller. They also raised the interesting point that I've been discussing with many of you in this room already, which is how we should define a tract. Should we define a tract if it goes to, well, if basically it has the same origin and termination, or is it the trajectory of the tract, or is it a combination of the both? Or something completely different. So that's an interesting point that is also raised in this paper. Now, I wanted to show you the image where I'm losing my anatomical references. So here they just show, sorry for the manic scrolling. They show seed regions and track the reconstruction between the axonal tracing and ex vivo monkey and in vivo human data to get the estimate of the best match. But the image that I wanted to show you is this one. So these are histological sections through a human brain at the level of the calcarine sulcus. So we're in the occipital lobe. And I know they nicely put in the different layers of the cortex, for example, but to me, as an untrained eye, I really struggle to see the separation between them, nor do I see like individual tracts or anything that is intuitively useful for me in terms of the anatomy, other than white matter versus gray matter. And that's what I mean. Like, you always need anatomical knowledge and you need to understand the method to the point that you know what you're looking at, which for histology, I have to admit, is not my strong suit at the moment. So I always need pointers when I look at histological slices to know my way around. That's basically it. As I said, it's quite a rich review. It's certainly worth a read. And you have some very beautiful pictures in there as well that make it very understandable what the point is. Right, that's the paper. Any questions, comments? Michel has his hand up.
Thank you, Steph. That was very interesting. So another review saying that tractography is not perfect, but you know, like no neuroimaging methods is perfect. I think like probably tractography is the only neuroimaging method where we just like, we should do better, guys. We're not perfect yet, because any other neuroimaging methods, they're like, no, this is correct. Forget about everything. This is the right way to do it. And I find this a little, you know, little annoying. So, you know, what do you think? Are we being too critical about our methods, or are the people too lax with their methods?
Well, I can't speak for other people, but it's, well, that's coming in. It's true that we are very critical when it comes to tractography. And that's, I think, partially owed to the fact that there has been a huge development in the last 15 years, basically, with a lot of new algorithms being thrown into the mix. We're pushing the limits of what we can do in terms of the acquisition with the scanners. We're pushing our gradient numbers. We're pushing the B-value. So there's just a lot that was ongoing. And we also started from a point where we didn't know as much, because the surface of the brain has been better studied throughout history in terms of we had labels and names for most of the areas. And then MRI was basically replicating what we know. But for white matter, there was only a limited group of people who knew about the anatomy of the white matter in detail. And then also because it was mainly mapped with postmortem or tracing studies, we never had a really complete picture of all the tracts in the brain, because you would miss them with different methods, right?
But so like we often take histology as a gold standard to compare with neuroimaging, but one might say that histology has its own problem. So the amount of time you expose your tissue to the staining, or like the distance from the injection, all of this is going to have an impact of how much you see the fibers. So,
which is what I really appreciate about this review, because they not only say tractography has its limitations, they actually go through each and every single method that has been used to validate it
Okay.
and say what's good, but also what's bad about it. And their conclusion is none of the methods are perfect.
Okay. And so they don't speak about spherical deconvolution at all?
Well, they speak about FODs, but not spherical convolution in detail. So even though there is the table that specifies the gradients and the b-value, the algorithm in the background, I think, comes a little bit short here in terms of the differences that you would see between a tensor model and advanced tractography models, and also the relationship between a higher b-value letting you resolve crossing at a lower angle threshold, those kind of things. But it's a very good point to get started, especially for juniors, to see what's out there and what the good and the bad considerations are for each of the validation methods.
Thank you. I just have something to add on this discussion is considering neuroimaging and the different types of neuroimaging which are which people are critics on, and more critics on tractography than others. One thing I'm thinking about this point is that tractography is basically a bit remote from the actual pure data in the term, or you are doing a modeling of a fiber using the diffusion that you measure. So it's not diffusion that you are directly using. It's not I think the thing that we are trying to the thing that makes it different is like you are modeling something that is not exactly the signal. You're not trying to extract more data from the signal. You're trying to use the signal to model something, which means that you can have a lot of different algorithms to do this modeling, a lot of different ways to interpret the diffusion data. And this is why you'll have a lot of variability between different methods and a lot of different critiques about what you can do with it when you compare to other methodologies about other neuroimaging techniques where you are trying to extract signal from the data. And I'm not saying that it's better or worse. I'm saying that in the mind of people, and my mind too also, actually, I have this kind of bias. It's more like when you are closer to the data, you're probably extracting something that is better, which is not necessarily true. But
which MRI method brings you closer to the data? Because you could argue the same for functional imaging or resting state imaging or whichever.
Well, no. Well, for me, functional imaging in general, you are trying to extract signal and denoise the signal that you have, and you're not trying to create depends on the it's a bit complicated, and I agree with that. It's not something that is clear cut all the time, but it still is. You're not making a brain from just the signal. You're trying to get a correlation between the signal that you have and the signal that you expect. And it's true, there is some modeling into that because the signal that you expect is modeled. But at least it's somewhere in the data. Like, I mean, I can see why you would have a critic, but this is my point of view. So I just express it like that.
Totally appreciate it. But I think that brings us back to Michel's question of, are we just more critical with our method and acknowledge these shortcomings, or is tractography worse than other methods? And I think it's the first one. We just discuss it a lot more than shortcomings in other methods.
Sorry. Yeah, for this, you hear me?
Yes.
Okay. No, only I usually use the electrophysiology, recording the local field potentials, and we usually have the same problems. Like it's really criticized because it's not only one cell, one neuron. You're not recording that activity, that electrical activity. You're recording like the field, and in that area also, it's really criticized the techniques. So I think also that each technique, if you don't use it, you criticize the others more. So I don't know. What I see is like that, and it's better if you use more than one technique in order to don't be so much criticized. No. Something like that.
I mean, personally, I think it's extremely valuable that we have those discussions and we're critical of the methods that we're using, because it shouldn't be a black box and you just blindly trust the method. What I think is potentially dangerous and damaging to the field and fundamentally reducing our own realm is that we come out with these papers attacking each other's methods, and they get picked up by the media saying neuroimaging doesn't work, which is not the case, but I think that's a very dangerous method to put out there. So I don't think that we should not be critical, or we shouldn't pinpoint the errors with each method. But the way we do it, I think we can improve. Leah, you have a question.
Yes, at one point you say that the authors suggest that the multimodalities was the way to go for comparing the methods. And I was wondering, can we really do this in humans, or is just for...
But not all of the methods. So obviously track tracing would not work in the human brain, but Klingler dissection or histological staining or polarized light imaging, cytoarchitectonics, myeloarchitectonics, like those things you could do in the human brain as well.
But we need like...
There's actually people doing it. It's not... Sorry.
Yeah, no,
it's not good. It's like you can.
But we need like a bank brain data, so you have to donate your brain postmortem. Yeah.
Yes, which is, and there's a big push for those kind of things. And it's coming more and more. If we look at the UK Biobank, for example, where they collect the data throughout life, and then for some of them also postmortem. But whilst I agree that having different methods in the same specimen is a good idea, we still need to optimize the methods in the first place. Like diffusion imaging ex vivo is a relatively new field still. And there is still a lot that we need to optimize and perfect to really have it give us information that is as useful and detailed as histology, for example, that has been perfected over years. So yeah.
Yeah, maybe like it's really interesting also just comparing diffusion imaging in vivo and ex vivo with, you say, like implementation of the ex vivo that I think like few laboratories do. Okay, thank you.
You're welcome. Victor.
So to expand a bit on the article,
I knew you're going to come back to it.
No. It's just now I'm changing a subject actually. It's more question for you, and maybe I can add something after. But do you think there is a method, or there will be a method, or you have an idea of something that would allow us to actually learn about the true fiber anatomy of the human brain in the future? Do you have any idea of if it's possible, or if we'll reach that one day?
Sure, we can reach it one day. It still will take us a while to get to that point. But it depends what you're interested in, as I said before. So if you just want to see the big, massive pathways in the brain, then we already have the methods to do that, postmortem and in vivo. If you really want to get all the details about tiny single axon connections in the living human brain, then we still have a long way to go for the human brain, at least. But yeah, I'm sure one day, like anatomy is not a dead science. It's very much alive and evolving and changing. And there's more and more people working on those questions and trying to resolve them, perfect algorithms, perfect how we integrate our methods. So I think there will be many exciting developments coming in the next couple of years and decades.
Okay, thanks. And there is just one comment that I want to add about on that, is that for me, one thing that is quite nascent still but is really interesting is about neurodevelopment and learning about how the brain actually wires this connection at the beginning. And when we understand that, we'll actually have, I think, way better models and a much better understanding of how one thing connects to another and why it's connected to it. And we could do like better informed tractography, for example, or at least have a wider understanding. So I think developmental neuroanatomy is something that is really interesting and yeah, has a great future. Thanks.
I completely agree. It's even more complex, I would argue, than the healthy human adult brain. But they also make the point in the review about in utero imaging with diffusion and how that has some shortcomings, and actually postmortem methods have shown that there is a lot more white matter than diffusion imaging suggested in the beginning. But that is very likely a methodological limitation because of the motion artifacts that then don't let you reconstruct the tract. But again, there's a big push for developmental, prenatal, postnatal tracking. So many things will come from it, I'm sure. Michel.
Yeah, regarding this neurodevelopmental research field, Pascal Rakic did that like more like 40 years ago. And so he did like different stage of development in the monkey brain, and the data set is available in person because it's not digital for anybody who would like to consult it and learn about how white matter connect those different regions and how things happen. I think he's one of the fathers of open science, really, as much as many other things, because he published more than 40 papers in Nature and Science. But I was thinking, like, I think we're asking too much to diffusion imaging, because it's a matter of resolution in the end. We're looking at axons that are a few microns, sometimes less than a micron, with big voxels that are like 1 cubic millimeter. Or if you're doing like neuroimaging in animals, like I do, you can get down maybe to 100 micron or 200 micron. But that's still a lot of different fibers in there that have complex configurations. So it is fundamentally different from tracing studies where you inject a virus or an agent that will follow those axons. The problem is you never have a comprehensive vision for it. I honestly don't think we can ever match the two. There is this paper in Nature showing that like a single neuron has 1,000 connections with the rest of the brain. That's just a mouse brain. Yeah, I'm sorry. It's just, we cannot ask too much to the method. We're looking at the big picture of how things are connected together, and people doing the staining and looking at the close picture of how one thing is connected to another. And mixing the two is, making us really humble about both methods. But we will never converge, I think.
Yeah, made me think about the fact that maybe the brain is what the philosophers would call a hard problem, meaning a problem that is actually so complex that or so out of our realm that it cannot be answered with the human means, because we won't ever have a method that are precise enough or computing power that is strong enough to actually model properly a human brain, or even a mouse brain for the matter, because it's just too complicated. There is just too many connections, too many things. Yeah.
Unless
then the question is,
unless people manage to organize themselves like the brain in circuits, very efficiently communicating things to tackle from a complex system another complex system.
I think I heard that before. Well, one thing I wanted to throw into that discussion as well is that it also depends on the question we're asking. Like, do we need tractography to tell us how the brain is wired up one axon at a time and all its detailed connections, or is it enough for the questions that we need to address to have a more big picture approach to how the brain is connected, and have clinically relevant measurements with that, for example? And then do we need to match them 100%? Probably not, but we need to appreciate where the caveats are for every single method and see if we can fill those caveats with the other methods to give a more comprehensive view of the anatomy of the brain. That's my take on it, rather than trying to force them brutally to give us the same information.
Yeah, I totally agree with you. Like, I think we have different methods, and everyone has its own pros and cons, and we, depending on what you want to see, you need to use different ways of looking at. So I completely agree. It's true that we can improve our method and make it then like better. But I think we always will have some methods that are better for some questions and others for another different questions. So yeah, completely agree.
There's a good comment in the chat that we should not underestimate scientists. How many things have been said that they were impossible in history and science did it? So yes, I totally agree with that, Chris. So let's do it. Let's map every single axon in the brain. It's going to keep us all busy for the rest of our lives.
You do it.
It's a team effort. You just said we all need to come together and share and work together. Right. Thanks for the discussion. Thanks for your excitement about the review. That's all we have time for today. So I wish you an exciting week in science, and we'll see you next Monday again. And I think Michelle is presenting next week. Fantastic. Looking forward to it. Have an